In 6.2, we're looking at one-to-one functions and inverse functions. A function is one-to-one if for any two inputs, x sub 1 and x sub 2, f of x sub 1 does not equal f of x sub 2. If we have the graph of a function, we can use the horizontal line test to determine if it's one-to-one. If we draw a horizontal line anywhere on the graph, if it doesn't cross or touch the function in more than one point, then the function is one-to-one. You may remember these diagrams and having to determine if it was demonstrating a function. For example, this one is demonstrating a function because every element of the domain is matched with exactly one element of the range. So, in other words, every domain element had exactly one arrow leading out of it. And it didn't matter for it to be a function that there were two arrows leading into 5. But because we have more than one arrow leading to a range value, this function is not one-to-one. If we have a set of points, we can tell if they're one-to-one by first looking to see if we have different x values. We do. And then to make sure we don't have any of the same y values for different x values. So this first one, all the y values are different. So no two x values have the same y value. So all the x values are different, so it's a function. And because all the y values are different as well, this is a one-to-one function. So in the second one, we have all different x values, so this is a function. We have a 0, a 1, a 16, and 81 as the y values. So all the x values get different y values. This is also one-to-one. In the last one, we have 2, -3, 4, and 1 in the domain. But here we see we have 2 6s in the range. So 2 goes to 6 and -3 goes to 6. So this function is not one-to-one. Here we have some graphs. So we can draw a horizontal line through these graphs. For example, this first one, this upside down parabola. So we see that this horizontal line intersects the graph of the parabola in 2 points. So the parabola is not a one-to-one function. This exponential function, though, if we draw a horizontal line, no matter where we draw a horizontal line, it will never intersect the graph in more than one point. So this exponential function is one-to-one. Here we have the square root function. If we draw a horizontal line, it's never going to cross it more than once. So this is also another one-to-one function. Okay, at the end of the last section, we looked at composition, and we looked to see what happened when f of g of x and g of f of x equaled x, and I had said that that would indicate that they are inverses. So that is a way to check to see if we have inverse functions. So let's try that using f of x equal to 3 minus 2x and g of x equal to -0.5 times x minus 3. I'm going to use red for my f of x function. I'm going to use blue for my g of x function. So first I'm going to find f of g of x. So I start by writing the f function, 3 minus 2, but instead of x, I'm putting parentheses, and I'll substitute in my g function, which is -0.5 times x minus 3. I'll simplify, so I'll distribute, and I get 3 plus 1 times x minus 3, or 3 plus x minus 3, which is x. So we now have that f of g of x equals x, but we do need to check it the other way as well. So we need to check g of f of x. So I'll start by writing the g function, -0.5 times x minus 3, but instead of x, I'm putting parentheses, and we'll substitute 3 minus 2x into the parentheses, we'll simplify inside first. So negative 0.5 times the 3's will cancel. We'll have negative 2x. And when we multiply that, we get x. So g of f of x also equals x. So that means these two functions are inverses. To algebraically find the inverse of a function, what you'll do is, if we have an f of x, you would change it to y. Then we'll switch x and y and solve for y. If a function is 1-to-1, its inverse is a function. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. That should make sense because to find the inverse, we're swapping x and y. Domains are usually the x's and ranges are the y's, so those two properties are switched for inverses. Graphs are symmetric with respect to the line y equals x. So if we had the graph of a function and the graph of its inverse, they would be reflections of each other over the line y equals x. Here's a function, f of x equals x cubed plus 1. Let's find its inverse. I'll change f of x to y, so y equals x cubed plus 1. I will swap x and y, so x equals y cubed plus 1. Notice the exponent didn't move, so just the x and y swap, so now y is cubed. Now I need to get y by itself, so I will subtract 1. X minus 1 equals y cubed. I'll switch it around since we're used to seeing y on the left. Y cubed equals x minus 1. I want to solve for y, so I will take the cube root of both sides, and y equals the cube root of x minus 1. F to the negative 1 of x is the symbol that's used to show that we have the inverse of f of x. So f to the negative 1 of x equals the cube root of x minus 1. Let's look at one more. So here we have f of x equals 4 over 2 minus x. We'll change f of x to y, so y equals 4 over 2 minus x. We will swap x and y. X equals 4 over 2 minus y. So we could solve this as a proportion and figure out y, or we could get rid of the fraction by finding the LCD. The LCD is 2 minus y. So we will multiply both sides by 2 minus y. We'll get x times 2 minus y equals 4. We'll distribute 2x minus xy equals 4. We want to get y by itself, so let's subtract 2x from both sides. We have negative xy equals 4 minus 2x. We'll divide everything by negative x. We get y equals 4 minus 2x over negative x. This is technically fine, although often you won't see that negative in the denominator. Instead, they might factor the negative out of the numerator and get the opposite of negative 4 plus 2x inside parentheses with the negative factored out. The negatives could cancel and we would have 2x minus 4 over x. So the inverse of f of x is equal to 2x minus 4 over x. You could also simplify it and divide out and have two different terms, like 2 minus 4 over x. Both are equally as acceptable.